Hi everybody, and welcome to a video on Bayes Theorem, arguably the most significant result we'll discuss in this course. First though, I want to briefly recap where we're at in the course. So recall that since week 1, we've been searching for a scientific inductive logic. That is a rigorous theory that will help us measure the inductive strength of arguments. In week 2, David Hume and Nelson Goodman taught us that justifying and even just formulating such a scientific inductive logic would be no easy task. In light of these challenges, we took a detour in week 3 to consider how pressing it actually is to develop a scientific inductive logic. Many biases or systematic errors that we humans are often prone to when it comes to making inductive judgments supplied motivation to think that we need to take seriously the project of crafting a scientific inductive logic that can help us correct for some of these biases. In week 4, we started off on this positive project by looking at some informal rules of thumb used to good effect by forecasters to make fairly reliable assessments of the inductive probability of arguments. And last week, we finally started to explore probability theory as an approach to inductive logic. In many ways, we can think of probability theory as formalizing some of the informal rules of thumb that we learned from Philip-Tetlock's superforecasters. This topic, the topic of mathematical probability and its significance for scientific inductive logic, will occupy us for the rest of the quarter. And today is really a highlight of this section of the course because we're going to discuss one of the most famous and significant results in probability theory, and that is Bayes' theorem. Alright, so let's get into it. Bayes' theorem is really a result that connects the probability of A conditional on B with the probability of B conditional on A. Now note first of all that in general, these two quantities are not necessarily the same, right? They might be in some special cases, but in general they need not be the same, right? For example, let's say A was the proposition that Fido is a mammal, and let's say B is the proposition that Fido is a dog. Then, right, you might think the probability of A given B, right, that is the probability that Fido is a mammal given that he's a dog, is 1, since all dogs are mammals, right? If we're given that Fido is a dog, then we know for sure that he's a mammal. Whereas the probability of B given A, right, the probability that Fido is a dog, just given the information he's a mammal, might be right less than 1, because there's other ways to be a mammal than being a dog. Right? So hopefully this example suffices to show that in general these two quantities are not necessarily the same. But Bayes' theorem shows that they can be logically related to one another if we know some other probabilities as well. So let's state what Bayes' theorem is. Bayes' theorem. This is a theorem that's named for the Reverend Thomas Bayes, who was a famous mathematician, probability theorist in the 19th century in England. Okay, the theorem is often stated in terms of the probability of a proposition H given a proposition E. Now, we don't have to use the letters H and E here, but we often do because we're often interested in the probability of a hypothesis given some evidence. So H stands for hypothesis, E stands for evidence we're given, right? We're looking for how strong is the argument that starts with some piece of evidence, E, and moves to some hypothesis H as a conclusion. Now, there's several forms that Bayes' theorem comes in, some simpler than others, and we're going to build up to them through things we already know. Right? So, first we can note that the probability of H given E is really equal to the probability of H and E over the probability of E. And this is just the ratio rule, right? You'll recall. And throughout, I'm going to assume that the probability of E is not equal to 0, right? E is a non-zero probability event or proposition. So that will allow us to apply the ratio rule. All right. Now, we know that the probability of H and E can be transformed into the probability of E given H times the probability of H. And this is our general conjunction rule, right? This holds for conjunctions generally. So this is general conjunction rule, where we're translating this, the numerator of this ratio. And then at the bottom we'll keep as the probability of E. So this is the first sort of version of Bayes' theorem that's going to be a handy one to have a grasp of. We can unpack it though a little more and get a slightly more complicated version of Bayes' theorem by unpacking the denominator a bit more. So again, I'll leave the numerator now as it was, the probability of E given H times the probability of H over. Now we can use the law of total probability on the bottom, which you'll remember from the video we did on deriving basic probability rules. And the law of total probability tells us that we can rewrite the probability of E as the probability of E and H plus the probability of E and not H, right? Because E and not H, or excuse me, H and not H form a logical partition, right? So this is a legitimate move to make. So this is by our law of total probability that we derived. Total probability. Now we can again employ the general conjunction rule to rewrite the bottom. So we get probability of E given H times probability of H all over probability of E given H times probability of H. Note that that's just the same. The first term of the sum on the denominator is just the same as the numerator, plus the probability of E given not H times the probability of not H. Right? All right. And now we have another version of Bayes' theorem here. Let's see. And this is by, again, another application of general conjunction rule. Now, we've related the probability of H given E to the probability of E given H together with the probability of H, and the other thing we need to know is the probability of E given not H. Right? Once we know the probability of H, we already know the probability of not H. So that one sort of comes in for free. All right, so this can be very handy, right, if we're trying to find the probability of a hypothesis given some evidence, and it's not immediately apparent what that conditional probability is, but it is much more tractable to figure out what the probability of E given H, how likely it would be to see the evidence given the hypothesis, right? If this is much more tractable to find than probably we're really interested in, probably the hypothesis given the evidence, we can use this together with information of the prior probabilities of the hypothesis to figure it out. So that's the beauty of Bayes' theorem. Now I want to write a slightly more general version here too. So here, right, in the third step where I applied the law of total probability, I used as our partition H and not H, but we really could have used a more general partition. So I'll state a more general version of the theorem here. So here we would have probability of H given E is equal to, and I'm going to cut down to that the second step there, probability, we know it's equal to the probability of E given H times the probability of H over the probability of the evidence. Now, I could rewrite that denominator using the law of total probability with any partition I choose. So I could use one that's more general than just H or not H. So I could let the numerator stay the same, probability of E given H times probability of H over, right? And now I could put in any partition here. So maybe we have, I'll say again, probability of E and H, and then I'll use any partition of which H is a member. So plus probability of E and, let's say, H1 plus dot 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 all the way through the probability of E and Hn. So now, right, I'm looking at the probability of the evidence and the hypothesis we're interested in, and also the probability of the evidence and other alternative hypotheses that are each incompatible with the hypothesis that we're considering, and which are together with the hypothesis we're considering exhaustive, right, in the sense that at least one of H, H1, H2, so on through Hn has to be true, and only one can be true, right, so that they form a partition, as we discussed in that video where we discussed the law of total probability. But now we can employ, again, the general conjunction rule. And we get here a pretty general version of Bayes' theorem, where we have on the numerator probability of E given H times probability of H. On the bottom, we have again probability of E given H times probability of H. And then plus, right, a term for each other member of the partition we're considering. So probability of E given H1 times probability of H1 plus so on through the probability of E given Hn times the probability of Hn. Alright, and this version of Bayes' theorem can be very handy for some of the problems that we'll be tackling where we're considering a number of different hypotheses, not just say two, right? H and its negation. We might be considering a lot of hypotheses, and this version will be helpful. All right, so that's Bayes' theorem. It's the derivation of Bayes' theorem. We know it follows from just basic principles that we've already derived in previous videos. Now I want to actually employ Bayes' theorem. Let's do some examples to see how it works and how it's useful. So let's first consider a simple example where let's say that let's say we're flipping a coin, right? And we have two hypotheses in this case. So this is a coin example. Our two hypotheses, let's say these are hypotheses about the bias of the coin. That is, how likely is the coin to come up heads versus tails on any particular flip of the coin. And let's say that we have two hypotheses. I'll call them H1 and H2. And the first hypothesis is that the coin is biased 1/3 toward heads, right? This means that it has a 1/3 probability of landing heads on any toss. And we'll say that the other hypothesis is that the coin is biased 2/3 towards heads. This means that it has a 2/3 probability of coming up heads on any time, and therefore only a 1/3 chance of coming up tails. So we know in this example, right, if these are our only two hypotheses, then we know that the coin is not fair, right? It's either biased towards tails or biased towards heads. We're just not sure which, right? Now, let's say that we start out thinking these are equally likely. So our initial probability for H1 is equal to our initial probability for H2. And since we consider these to be exhaustive, we'll say that that means their probability is 1/2, right? Since they're, H1 and H2 effectively form a partition here. All right, so now we know the probability of each one at the start is 1/2. But then let's suppose that we get some data, right? Or we get some evidence. So I'll maybe write it as E, our evidence proposition. Let's say we flip the coin 3 times and we observe that we get H, H, T. So we get heads, heads, tails, right? That's our evidence. Now we want to know what's the probability of each of the hypotheses being true given that evidence, right? So in the first case, what's the probability of H1 of the probability being biased 1/3 towards heads given E, right? Given that we saw heads, heads, tails. Now, you might think, right, it should be a little bit lower intuitively, right? Because we just saw heads, heads, tails, right? And that conforms a little better with the idea that the coin is biased in favor of heads, right? So that'd be H2, right? Rather than being biased in favor of tails, because we see more heads here than tails. We see 2 heads and we only see 1 tails. So we should suspect that this probability is going to end up being less than 1/2. Right? But it's not immediately right, or at least for me, it's not super intuitive to immediately see, like, well, what is that conditional probability, right? This is the exact sort of case where we'd want to use Bayes' theorem if we can, because, right, we're trying to compute a conditional probability. It's not immediately apparent what that conditional probability is, but it is more intuitive what the reverse conditional probability is, what the probability of the evidence given the hypothesis is. So let's try to figure that out. Probability of H1 given the evidence. What would Bayes' theorem tell us? Well, Bayes' theorem, remember, would tell us that this is really equal to the probability of the evidence given H1 times the probability of H1, prior probability, over that same thing, probability of E given H1 times the probability of H1 plus the probability we would see that evidence given our other hypothesis. In this case, there's only one other hypothesis. It's just that H2, the coin is 2/3 biased towards heads. So given H2 times the prior probability of H2. Okay? That's what Bayes' theorem tells us. Now let's go through this and make sure that we know each of these terms, and so we can solve for it. So we know the prior probability of H1, right? That's 1/2. Now the probability of the evidence that we've gotten given H1. So we suppose that H1 is true. We suppose that the coin really has a bias of 1/3 towards heads. And now we ask, how likely is it that we would see heads, heads, tails, right? Well, the probability we would see heads on the first time, right, is 1/3, because we say that the bias is 1/3 in this case. Probably we would see heads on the second time is again 1/3. Probably we would see tails on the third time is 2/3, right? Because the coin is biased 1/3 towards heads, it's biased 2/3 towards tails. So the product of these three will give us the probability that we would see that evidence given the hypothesis, right? And now we'll look at the denominator. The first term of the denominator is the same as the numerator, and that's always the case when we're using Bayes' theorem, so that's nice. 1/3, 1/3, 2/3 times 1/2. Plus, now, we know the prior probability of H2 is 1/2. We thought that was just as likely as H1 to begin with. Now, how likely is it we would see this data, that we would see heads, heads, tails, given that the second hypothesis is true, that H2 is true? Well, H2 says that the probability of getting heads on any flip is 2/3. So the probability we would get heads the first time is 2/3, times the probability we get heads the second time is 2/3, times the probability we would get tails on the third one is 1/3 this time. Right? Okay. Now, let's see what this all computes to. So we have 1/3 times 1/3 times 2/3 times 1/2 on top. So the 2's are going to cancel out there. We're going to get, what, 1 out of 27 on top. On bottom, we're going to get 1 out of 27 again here, plus 2 out of 27, which is just equal to 1 out of 27 over 3 out of 27, which is just equal to 1/3. So this means, right, that the probability of the hypothesis, given that evidence, given HHT, the probability of that first hypothesis that the coin is actually biased towards tails has gone down to 1/3. Right? And we can then infer from that the probability of the other hypothesis has to be 2/3, right? So the probability both of them together has to add up to 1. So, right, we've used Bayes' theorem to figure out a precise value for this conditional probability, right? The probability of getting, of the first hypothesis, H1 being true, given the evidence, right? And it wasn't immediately apparent what that conditional probability was, but by unpacking it in terms of Bayes' theorem, we were able to solve for it. I'm going to do one more example of Bayes' theorem in this video. Let's do a medical example. This is sort of timely, given all the medical testing that we're talking about in the news. Let's see, medical example. Okay, suppose that we're wondering if a particular individual has a disease. So I'm going to let D represent the proposition that some individual X has a disease, right? This particular disease that we're interested in. All right. Now let's say that the disease is fairly rare in the population. So without giving this person a medical test, the prior probability that they would have the disease is pretty low. Let's say it's maybe 1 in 1,000, right? So this is not super rare disease, but fairly rare. Now let's suppose that we have a medical test, right? And I'll use plus to represent the proposition that X gets a positive result on the test, right? The test intuitive, right? Getting a positive test result means it's right saying that you do have the disease. Getting a negative test result is a test saying, oh, you don't have the disease, right? Now, let's suppose here, right, and I'll use minus to represent that X gets a negative test result. So that means, right, negative is just really equal to the negation of positive. Right? Now let's suppose that this test is reliable in the sense that the probability that you would get a positive test result, given that you actually have the disease, is reasonably high. Let's say maybe it's 0.99, right? So 99% of the people who have the disease will test positive, right? If we suppose you have the disease, that supports the claim that you're going to test positive to degree 0.99. And let's suppose that the probability that you would test positive, given that you don't have the disease, right, is very low. Let's say only 1%. Only 1% of people who don't have the disease test positive. So given the information that you don't have the disease, that would support the claim that you are going to test positive to a very low degree, right? Only degree 0.01. Okay, now let's suppose that we take a particular individual and we test them for the disease and we get a positive test result, right? Now what we really want to know is what's the probability that they have the disease given a positive test result, right? Now note, right, it's important that this is not in general the same as the probability of getting a positive test result given that they have the disease, right? This is like the example that we came up with at the start with Fido being a mammal and Fido being a dog, right? In general, right, a conditional probability A given B is not the same as the probability of B given A, right? So we don't want to fall into that confusion. And actually, falling into that confusion is related to committing what we call the Bayes rate fallacy or Bayes rate neglect back in our videos in week 3. So we don't want to do that, right? What we do want to do is employ Bayes theorem here, right? It's not immediately apparent how likely this individual is to have the disease given that they got a positive test result, but we do know how likely it is to get a positive test result given that they have the disease. So let's see if we can use Bayes theorem. So by Bayes theorem, this is going to be the same as the probability of getting a positive test result given they have the disease times the probability that they have the disease, the prior probability, over that same thing, right? Probability of positive test result given the disease times the probability of having the disease plus the probability that you get a positive test result given that they didn't have the disease times the probability that they didn't have the disease, the prior probability. Okay. Now let's see if we can figure each of these out. So we know the probability of getting a positive test result given that you have the disease is 0.99. And we know the prior probability of the disease is 0.001, right? That's the base rate of the disease in the population, 0.001. So we're not neglecting that, right? We're factoring that into the formula. On the bottom, the denominator, we're going to have that same thing, 0.99 times 0.001 plus, now, what's the probability that we would get a positive test result given we don't have the disease? That was given as 0.01, right? Fairly low, times the probability of not having the disease, the prior probability. Well, here we can use negation rule to figure that out, right? That's just 1 minus probability of having the disease, which we know is 0.001, right? So now we can just plug this into a calculator if we wanted and figure out what the answer is. Okay, and the answer comes out to around 0.09. If I plugged everything into the calculator, right? So this is actually interesting, right? This shows that the probability that you have the disease given a positive test result is actually still fairly low. So in this case, we would say this test is not very diagnostic, right? Even if you get a positive test result, it's still more likely than not that you don't have the disease because of how low the base rate of the disease is in the population. All right. There's a nice way maybe we could think of Bayes' theorem in a picture form that we'll close on. That might help us see what's going on here. At least I'd like to think of probability in this sort of geometric fashion sometimes. So let's suppose that we have this space of points that represents different ways the world could be, different possibilities. And let's say that we have two hypotheses, and this region here is one hypothesis, the big region, H1, and the little region is some other hypothesis, H2. So H1 has much bigger prior probability than H2, right? Now let's suppose, right, that we're looking for all the points in the region that have some further property to them, call it X maybe, right? We'll say X is like the union of these two regions. Now, right, what we can see here is, right, the probability, given how I've drawn things, the probability of X, given that you're in the H2 hypothesis, is more likely, it's greater than the probability of getting X, given that you're in the H1 region, right? A greater proportion of the H2 cases involve X being true than the proportion of H1 cases that involve X being true. And yet, right, it's plausible given the way I've drawn it that it might still be the case that the probability of H1 given X, if we're just told we're somewhere in the X region, the probability of H1 given X might be greater than the probability of H2 given X, right? Because the H1 region is so much larger than the H2 region, right? So this shows that you can have this sort of reversal happen here. All right. Well, we'll get some more practice with Bayes' theorem. We'll be using this a lot on homeworks and exams. Actually, the upcoming homework has some earned problems that require to use Bayes' theorem. In the next video, we're going to use Bayes' theorem to come up with a really simple solution to a very famous problem in the history of probability, the so-called Monty Hall problem. So that's what we'll do in the next video. Thanks for watching. Please remember to complete the participation poll for this video, and I'll see you next time. Thanks, guys.